All right, everybody. Today we're going to be reviewing functions and basically parent functions that we're going to be talking about again before we start learning a whole new equation here. So functions that belong to the same family share characteristics. The parent function, which is something that we've talked about in the past before, is the most basic function in a family. Functions in the same family are transformations, aka moves, of their parent functions. So here's what we've been talking about in the past. First of all, if we're talking about a parent function, first of all, has no extra numbers. That's the first thing. That's how we recognize a parent function. It has no extra numbers. We'll just write that for short. The other thing that we know about a parent function is, there are no negatives either. So no negatives in a parent function. And so right below here, you can kind of see the parent functions that we've been talking about. These are the ones we've learned in the past. We have one other, the cubic function, that we'll mention shortly here. But when they talk about this idea of a transformation, remember, a transformation can be a couple things. It can be a reflection, or as we said in class, a flip. We can either also move it. We can move it left. We can move it to the right. We can move it up, down. So these are all the different things that we've done. In fact, in our word wall, in our most recent word wall that we're going to be looking at in Unit 6, does have all these graphs here. And it does have, you see, it has the square root. That's going to be the new one we learn in this unit. It has the quadratic. We have the cubic function. That's the only one that was missing in this chart. We have the absolute value. But remember, it's for these functions here. These are the parent functions. Throw that into our word wall as well. It's our parent functions that then follow these rules for translation. We've talked about thinking opposite, as you can see here. For anything that says an H, notice how it's inside the actual function. But we think opposite. We see a plus, it's left. We see a minus, it's right. We see numbers on the outside, and it's exactly what it looks like. If it's adding, then we go up. We're subtracting, we head down. But this was the most important one. The fact that if you see a negative in front, because that's where it all begins, right? We look in the beginning of a function. But if we have a negative in the front, it just means it's a reflection on the x-axis, which means all of these just get flipped over. So we have a parabola opening down. We have a cubic coming down this way. We have an absolute value opening down if there's a negative value there. Now, we talked about vertical stretching and shrinking as well, and how we use that and approach it. So let's talk about some of these parent functions there. So we'll revisit that word wall because we are going to need it. So here are the parent functions that we've already learned about in class. So again, we're going to talk about the family they belong to. So for instance, the first one here is a constant function. And we recognize a constant function because it has no x in it. Now, I understand you look at this and go, but it says f of x. Yeah, but the function itself here doesn't have an x. Remember, we can even call it y equals 1. Instead of writing the function notation, we could write it with a y, but it has no x variable. Or you can think of it this way. If it has no x variable, you can also see it as it does have an x, but it's a power of 0, which is why we don't see it. But when you're dealing with a constant function, remember, this is just what we call a horizontal line. They go side to side, depending on what y value we're touching, but it's basically just a horizontal line. Again, these are all equations that we've already dealt with in the past, so we are refreshing your memory because it has been a while. The other thing I'll mention is they do say domain and range. Just remember your domain. These are your x's. Your range, well, these are your y values. And so one of the things to know, well, actually, let's revisit that later. Let's talk about the functions first. We'll mention that in a bit. All right, so then we have a linear function. And when you have a linear function, well, look, we finally get an x. And of course, we could also just call it y equals x. But the question is, well, what is it that makes it a linear function? A constant has no x in it. A linear function has an x in it, but there's that invisible power of 1, and that's it. It's that tiny detail, that power of 1, that tells me that something is linear. So if the greatest degree, right, the biggest power you see is a power of 1, that's how we know something is linear. And so we get things like this. Now we also know that lines can head down, right? They could go in the negative direction as well. So we're dealing with just lines. But when you're talking about the parent function, look at that. This is what we mean. It has no negative. It has no extra numbers. We're not talking about powers. But then there is one nice thing about a parent function. There's a lot of points they always have in common. So like right here, we see 0, 0. It goes through that. It also goes through 1, 1. And it goes through negative 1, negative 1. So you're going to see a lot of similarities within the points when it comes to a parent function. All right, well, now the next one. The next equation that we have here, the next parent function, is going to be the absolute value here. And when you're working with the absolute value, well, here's our function. Remember, it could also just say y equals the absolute value of x. It could look like this. This is the one that we like to call the v function because it just kind of has the shape of a v. It is very linear because it does have a power of 1. But remember, an absolute value makes everything positive. So that's why we don't see anything below the x-axis. Everything's above it because everything is positive. But the question is, well, how do you recognize an absolute value? Well, it's not because of a power of 1 or has no x. It's physically these lines, right? These are the lines that tell me that I'm working with an absolute value. So we'll just make a little note that it must have those absolute value lines right there. There's stuff inside there, but these are the lines, right? So it's one of the easier ones to recognize. Okay, and then the next function, of course, is a quadratic. We did a lot of quadratics last year. It's probably our biggest unit. It says f of x is equal to x squared, which, of course, we can also say y is equal to x squared. But again, look, there's no number being added or subtracted. There's no negative in front. That is why this is the most basic of all quadratics. That's why this is the parent function. But here's what I want you to notice. When it comes to points, remember when we talked about the linear function, it goes through 0, 0, 1, 1, negative 1, negative 1. Well, look at this one. Also hits 0, 0. Right? That's kind of our vertex. It also goes through 1, 1, and it even hits negative 1, but it's positive 1 because everything is positive with an absolute value. Well, look at your quadratic. Your quadratic also has this very important vertex here called 0, 0. It also goes through 1, 1. So you see there's a lot of similarities within the parent. That's what happens when you don't have a value. And this one is also negative 1, 1, just like this one, except as soon as we have a power of 2, we have to start curving, right? So we have a curve in our polynomial. Yet this one was not a power 2, that's why it's still very linear. But there are a lot of things that are very similar to each other here. And again, this one does have a special name. We do call this one a parabola. Let's not forget that. That is the special name for this equation. All right, but there is one more, and I want to throw it out there because it is one of the graphs that we've learned. It's part of this new family of functions. And the graph that we're talking about is the cubic. And don't forget that when you're working with the cubic function, we're talking about f of x is equal to x to the third, or we could say y equals x to the third. But just keep in mind, this is the function that looks like half a parabola heading down, but then half a parabola going up. But look, just like the others, it goes through 0, 0. It goes through 1, 1. And it also goes through negative 1, negative 1. I know I didn't draw the x and y axis. It doesn't matter. I just need you to see these points. There's a lot of similarities when it comes to these points when it's a parent function, again, because there's nothing adding or subtracting. There's no negative in front. But these are the most basic equations that we can have. All of these here. Now, speaking of domain and range, we said I would come back to it later on, so, well, here we are. When you're dealing with domain, one of the first things that we should be aware of is that we're dealing with all the x's. Well, remember, this thing goes to the left forever. It goes to the right forever. That's why my domain is all real numbers. There are no issues with x's. Even this graph, it goes to the left forever. And again, if you're thinking, yeah, but it's heading down. No, no, no. It's heading down and left. That's why it's slanted. So it goes left forever. It goes to the right forever. That's why it's all real numbers. The absolute value, same thing. It goes to the left forever. Look at that, up and left. And it goes to the right forever as well. So all real numbers. Quadratic, same thing. Even though you say, but it's going up. Well, it's slanted. It's going up and left. That's why it's slanting over. This one is going up and to the right side as well. So that's why it's all real numbers. And for the cubic, same thing. For the cubic, we're dealing with the same functions. So notice, anytime they ask you for a domain, it's always going to be all real numbers. We have had one issue towards the end of last semester where we saw that change. But for the most part, most of our functions, our domain is all real numbers. So now the only thing left to talk about is your range. When we talk about range, we're talking about the y value now. And so when you have a constant function, well, remember, it's constant because it never changes. So if in this example it says y is equal to 1, then it only touches that y value over and over and over. So our range is y equals 1. When I look at this one, the graph goes down forever. It goes up forever in this direction. That's why we get an all real numbers. When I look at the absolute value, it goes up forever, but it doesn't head down forever, which is why our range is y is greater, because it goes up forever, greater than 0. And same thing here with the quadratic. It goes up forever, it never goes down forever. So then we say y is greater than or equal to 0 because 0 is the lowest this gets. Now, if we were talking about domain and range on this one, well, again, same thing. It does go to the left forever. It goes to the right forever. So this would be all real numbers. And then if I'm talking about range, well, look, it goes down forever. It goes up forever. Then this one would also be all real numbers. Again, these are all the parent functions. There's one. I know there's still one that we did with a fraction, our rational expressions. Here, these are all of our basic parent functions that we're going to be working with. And those are the ones that we see in the word wall, except maybe for these two. So if these are the parent functions and we know what they're supposed to look like, well, what happens when we start bringing in numbers into the mix? So that's what we talk about, and we call it a transformation. So it says a transformation here changes the size, the shape, the position, even the orientation of a graph. And by orientation of a graph, remember, I could have a parabola like this, but if I give it a negative, then it could look like this. That's what they mean by changing the orientation. It's facing in a different direction, is one way of saying it. Now, a translation, just a translation and nothing else, a translation is a transformation that shifts the graph horizontally or vertically, but it does not change its size, shape, or orientation. So these two words are slightly different, right? A transformation, by the way, it only occurs when numbers, forgot about these graphs, join the parent function. Remember, the parent function has no extra numbers floating around, no negatives, but as soon as you start bringing numbers into the mix, a transformation will occur. But remember, a transformation can change the orientation and even the size of it. A translation does not, right? That's the key. A translation does not change its size, shape, or orientation. A translation can only do one of two things. It's either going to move it, according to them, when it says horizontally, it's either going to move it, let me get one that works here, it's going to move left or right, and remember, this is where we think opposite. According to the word one, everything we did last semester. So we're reviewing again because it's been a while since we've mentioned this. And you can move it vertically, which means you're going to move up or down. Move up or down. Right? That's our K value. And remember, it's exactly what we see. This one we think opposite, and it's exactly what's there, whatever it says. So we're going to put it into practice. Now we are going to be practicing how to draw the parent function. And once I draw the parent function, then I'll do the new function. So we're going to be doing two things, okay? So it says graph g of x. G of x is equal to x minus 4. All right, first thing I do, I look at it carefully. Here's the function they want me to draw. And the first thing I look at is, look at that power of 1. Just by looking at that, I already know this is a line. I know what it has to look like. So they said, draw me this and its parent function. Well, the parent function is going to be a line, y equals x. So it's the most basic of all lines that there is. So it's linear. I'm going to do this. I'm going to go 0, 0, 1, 1, and -1, -1. So now, of course, I'm going to take my little Metro card here, draw my line as best as I can. Remember, this is the parent function. So this is the one we call y is equal to x, the parent. All right, well, the parent is done. It's been drawn. So now the question is, okay, well, what's that -4 going to do to my function? All right, well, let me write it down. It says g of x is equal to x minus 4. Now, remember what we've said. This is not in a parentheses, so this is not an h value. This is my k. And if this is my k and it says -4, then there's only one thing I'm going to do. I'm just going to move everything down because it's negative 4 spaces. That's what I want to do. And so they said, when they say, hey, tell me the transformation, you just describe what you're going to do, but this is our k value. We're dropping it down 4. So here we go. Get a new color here. So all I'm going to do is I'm going to drop it down 4 spaces. So I'm going 1, 2, 3, 4, 1, 2, 3, 4. See, 1, 2, 3, 4. So all I do is I drop it down to here, here, and here. I'll get my card. Remember, I'm still just drawing a regular old line, but we're going to have 2 in our picture. This is the parent right here. This is the one that I called g of x. That's the one they wanted me to draw. And now that I'm looking at it, well, the next thing they want me to do is they want me to say, okay, well, what's your domain and what's your range? Well, my domain are my x's. So does it go to the left forever? Remember, I'm just talking about this reddish one here. Does it go to the left forever? Absolutely. Look at that. Remember, it doesn't go down. It's going down and left. So it goes left forever. Does it go to the right forever? Yeah, that's why it's slanting this way. So it goes left forever, down forever. Sorry, left forever, right forever. Then my domain is all real numbers. And now I'm going to do range. Well, when I'm talking about range, these are my y's. So my question is up forever, down forever. Just like for my domain, I'm thinking left forever, right forever. That's what I'm asking. Well, let's see. For my y's, does it go down forever? Yes, it does. Does it go up forever? Yes, it does. Then my range is all real numbers. And remember, you have this note appear at the top to show you how you should be describing range. I know this is just for the parent, but when you do your new ones, they should match up what you did here. And there you go, that's it. They wanted me to describe the transformation. We did that. That's as simple as that. And then I did domain and range. All right, so let's try another one. Let's see what happens next. So let's flip the page here. All right, so now they want me to talk about a reflection. So a translation is a move. That's what a translation is. It's just a move, nothing else. So now that I'm looking at this one, they're saying, okay, well, let's talk about the word reflection. And let's see what that entails. So a reflection is a transformation that flips. There's the key word. It flips a graph over a line Okay, so it flips it over a line called the line of reflection. All right, so a couple things that we might want to add here. So we call the line of reflection. A reflection, they said, is a flip. And back in geometry, we used to say it's like flipping it over a mirror. There has to be a mirror image. That's what they mean by this, and that's what we call the line of reflection. So that's why we always kind of assume we talk about mirrors here. So it is a reflected point, which is the same distance from the line of reflection as the original point. That's why we call it a mirror image, sorry, but on the opposite side of the line. So again, the best way to show you is with an example here. So we're going to graph p of x is equal to negative x squared and its parent function. All right, so I'm going to do the same thing that we did earlier, okay? First of all, I'm going to highlight my equation. Notice how I did not highlight the negative number. Remember, parent functions do not, right? Parent functions do not have negatives. Parent functions do not have extra numbers. That means the parent function is just x squared. That's my parent function for this one. So it's a quadratic, and it's y equals x squared, just like I see here. Now, I know that for mine, the one that they want me to do is, they said p of x is equal to negative x squared. So I'm going to start by drawing the parent. Now, we already know the points that the parent goes through. That's what I showed you earlier. We know that all parents go through 0, 0, 1, 1, but because it's a quadratic, we also know it goes through negative 1, 1. So here is the parent function. I'm just going to draw it dotted so we don't confuse it with our real answer here yet. There's the parent, y equals x squared. But again, I wanted to give you some random points so that we can see them. Now, the question is, well, what happens when you have a negative in front? So what does the negative here do to the function? Well, according to your word wall, it says it right here, when you have a negative in front, just like I see it right here, that's my description. These are the words I need to write out. It's a reflection across the x-axis. Remember, they want you to describe the transformation. So that's all I have to do. All I have to do is say it is a reflection across the x-axis. Again, use your word wall. If you forget, how am I supposed to say it? Well, it says it in your word wall. Nice and simple. Now, what does that mean? Okay, well, that means that I have a mirror, and the mirror is the x-axis right here. And so when we do a reflection, remember, this just means it's going to open down. So if it's going to open down, remember, this dot is going to be in the same spot. That can't change. But you see how this one is one space away from the mirror like this? Well, then I have to go one space away from the mirror in the other direction. And there's my first point. Well, this is actually the first one because it's already there. But then I do the same thing over here. This is 1 point away from the mirror, 1 point away from the mirror. And there it is. There's my reflection of this quadratic. This is the one they want me to call P of X. All right, so the only other thing they want me to do is name the domain, give the range, right? All right, well, we already said domain are your x's. So if your domain is your x's, you got to ask yourself, left forever, right forever, right? This is the question we ask for domain. Well, does this graph go to the left forever? Yeah. Again, it doesn't just go straight down. It's slanted. Left and down is what it's doing. So it does go left forever. This one goes to the right forever. Yes, we just said yes to both. Then my answer is all real numbers. And then, of course, over here, when we talk about the range, well, let's talk about this one here really quick. All real numbers, right? Left and right. For range, we're talking about y. So the question is, does it go up forever? And then does it go down forever? Is the question we ask ourselves here. All right, well, Does it go up forever? No, it doesn't. When you say no to one of these questions, then you're going to write your y. And does it go down forever? Yes, it does. So because it's heading down forever, we say y is less than. But there is a dot right here, so we do have to say equal to. And so if it goes down forever, then the question is, well, what's the highest y value? See, I'm on my y-axis. What's the highest y value it gets to? Well, there it is. It's 0. So we write it in this form. Again, when it got flipped over, you're describing how it behaves along the y-axis. All right, so there's our example for this one. So negatives will flip it over, and we can always do a mirror image of it. And remember, adding numbers, subtracting numbers, depending on where it is, that's what's going to tell me where to draw the function. So one more thing before we give you a moment to try some of these problems out. We're going to review vertex form. Again, vertex form is what we see in the word wall for every single one of our parent functions. And so here it is. It says, let me give you darker color here. Y is equal to, now I'm going to give it to you in function notation, f of x plus or minus h, it just depends if they're adding or subtracting, plus or minus k. And just remember, depending on what they give me, if they're talking about the k, we already said, if a number, and we're calling it k for now, right, just to represent it, if a number k is outside the function, I'm just going to say parentheses, right, because you see it's outside of a parentheses here. Then if it says plus k, then you're going to move up. But if it says minus k, well, then that just means you're going to move down. So this is what we mentioned earlier. Same thing on this one. When you have something that says plus or minus, and now notice where the h is located, right? When we talked about the k right here is outside the function. But when you look at your h, well, your h is inside, right? Inside the actual function or inside the parentheses, however you want to think about it. Okay, well, what do they want me to do because of this information? So the idea is if number h, right, whatever that number is inside. Now I'm just going to say parentheses for now, but it could be inside a function. If it's inside the function, then don't forget, if it says x plus h, I'm actually going to move left. I know there's a plus, but we've talked about thinking opposite for this one. And if it says x minus h, well, then I'm actually going to move to the right. And again, just like we mentioned before, this is the only time you think opposite. All right, so one of the things that we're going to ask you to do, like for these problems at the bottom, in fact, let me do one with you, and then that way we'll give you a chance to try the other two on your own. So we're going to use this idea here, and it says, graph the function and its parent, then describe the transformation. All right, well, look, let's do this one in the middle. They're calling it h, but remember, if you want to spot the parent, here's all you do. The parent is the letter. Nope, no adding, no subtracting, no negatives. So that means, there it is. That's the parent right there. We now know this is a quadratic. So the parent is simply y equals x squared. All right, well, we talked about how to draw this thing already. The parent is 0, 0, 1, 1, negative 1, 1. There it is. I'll make it like this because it's just the parent. And we want to describe how it's changing for us. All right, so there's the parent. Y equals x squared. So now let's talk moves. And by moves, I'm talking about that number right there. So that's why when you look at what we just wrote here, it says, is that negative 2 in a parentheses or not? Well, clearly it's in a parentheses, so it's inside the function. And if I have to think opposite for this, remember it says x minus 2. Well, then right away, I already know how I'm going to do this. According to that -2 right here, I'm going to move. Well, what direction here? We're moving to the right. We're going to think opposite. I'm going to move right 2 based on what we see here. So this is not the first time we do this. We've done this before. So all I'm going to do to my graph is move every point over 2 spaces. And then this one, 1, 2, so it's right here. All right, well, there you go. This one right here is the one that I will officially call, well, the official name they wanted me to call it was h of x. So there's h of x. And now I'll answer all the stuff that they asked me to do at the bottom. Now notice they said, give me the transformation. We actually already did that. We said we moved it. So we move, or we could say translate, move, right, 2, that's it. That's all we did. Okay, domain, that's left and right. Left forever? Absolutely. Right forever? Absolutely. Remember, they don't shoot straight up. They're slanted. So then, all real numbers. And then, of course, it asks for the range. All right, well, if you're going to do the range, well then, does it go down forever? No. But it goes up forever, which means we're going to say y is greater than or equal to, because it goes up forever. And remember, what's the lowest y that it gets? Well, this is the dot right there, the vertex. And look at that. The lowest y is 0. So that's what we're going to be doing. All right, so we're going to give you a moment here. We're going to pause the video so that you could try these two. Again, you are drawing the parent, speaking of the moves, and then you can answer domain and range. All right, let's take a moment to do that and pause the video now. All right, it's time to check your answers here. So if you look carefully, remember, we highlight the letter. This one had no power, nothing else. So the parent is y equals x. Here it is, right? Going through my usual points, 0, 0, 1, 1. So the 3 that's there, it's not in a parentheses or anything. That means up and down motion. So up 3, there's the drawing. And because it's linear, we automatically say all real numbers for domain and your range. And of course, we just say that we moved up 3. This one, on the other hand here, when I highlight, yes, I see the absolute values. I have to highlight that and the letter. But when we're looking at it, we draw it out. So here it is. Here's the parent, the absolute value. But the negative in front said you had to flip it over. All right, well, there it is. We have flipped over that absolute value. It's going in the opposite direction. There's the official name, n of x. Now, my domain is left forever, right forever, all real numbers. But this one doesn't go up forever. It does go down forever, which is why we say y is less than or equal to 0, because 0 was the highest this one went. Now, what happens when we have a number here? Not just a negative, but we actually throw a number out in front. So that's when we look at the other side and we realize, okay, the other thing, and the last thing that we mentioned about these graphs was another way to transform the graph of a function is to multiply all of the y coordinates by the same positive factor other than 1. When the factor is greater than 1, the transformation is a vertical stretch. When a factor is greater than 0 and less than 1, then we're going to get what we call a vertical shrink. All right, so there's a couple things that we're going to highlight here. So when you multiply all the y coordinates, okay, and then it says by the same, I should say, by the same positive factor. And it says other than 1, because the 1 doesn't really do anything. So one thing you should make notice of is that only y gets multiplied by a number, not the x. We don't affect the x in any way. It's only the y value that has that. They also said that we could have something called a vertical stretch, but I'm only going to have a vertical stretch if the factor is greater than 1. So that means that for these, for a vertical stretch, the a value that they're going to give me is greater than 1. And so the graph is going to get more narrow. Oh, there we go. Narrow. As we've seen in the past. Some people say, oh, it looks like it got skinnier. Whatever you want to call it, right? But then, of course, we could also have a graph that has a vertical shrink. And that's when you have a factor that is greater than 0 and less than 1. So basically, your A is between 0 and 1. So we have an A value between those two numbers. And so some people say that it gets wider. Now, we did do it a different way earlier, so I am going to remind you, I'm going to show you that there are two options for doing this. And so we'll do the first one the traditional way they want me to, okay? All right, so graph each function and its parent. All right, first let me locate the parent for example number 3 here. So in example number 3, okay, here's my function. Remember, parent functions have no numbers. That's why I'm not highlighting the 2. So just like in the example right there, the parent function is y equals the absolute value of x. Now, here's what they want me to do with this, okay? I'm going to make a little table for the parent. We already know what numbers the parent is going to go through. It's going to hit 0, 0. There it is. It's going to hit 1, 1. So 1, 1. It's going to hit negative 1, positive 1. These are the points that all parent functions for an absolute value will always make contact with. And then I'm going to do a rough sketch because that's what they want. They said, okay, sketch it out. All right, so here it is. So here's the parent. And we're not doing it all solid just so that we could tell the parent apart from the new one, right? The new function that we're going to call g of x. All right, so now the question is, what does that 2 in front do? Remember, it's not inside. It's not moving up, down. It's not moving left, right. When we have a number in front, well, first of all, your A is equal to 2. So that's bigger than 1, right? Look at that. It's greater than 1. So we have a vertical stretch. So when we had a vertical stretch, here's a different technique that they're telling me to do up here. They said, multiply your y's by the same positive factor. Well, it's my 2. That's what I'm going to multiply everybody by. Again, only the y's. So what they want me to do is, they want me to multiply all of these by 2. And then this will create a brand new little table for me. So this is one way of doing it. See, your x's, we never said we were going to mess with them. Only the y's are getting multiplied. So this is 1 times 2 is 2. 0 times 2, well, that's still 0. And then 1 times 2 is 2. Now all I'm going to do is plot these points and draw my graph. Negative 1, 2. Remember, it's called the vertical stretch. We said it was going to get narrow or skinny. 0, 0. Okay, there's 0, 0. And 1, 2. 1, 2. And now that I've done that, well, here's my answer. And look, that's why people say, oh, it looks like it got a little skinnier. Well, yeah, that's exactly what kind of happened there. Look at my absolute value. The arms of the absolute value actually got closer to each other. But this is the one they want me to call g of x. So that's what they mean by getting, oh, it got skinnier. Now, we did it differently before. And so I do want to remind you that that is still an option. When we say your a value is 2, remember, all we said was put a 1 under it. And if you put a 1 under it, that means you're going to count 2 up, 1 over. So check it out. Here's 0, 0. You go up 2 and 1 over. And that gives you this point. Well, then you also go to the other side. We kind of make like this T shape here. So we could have done it, and yes, you can continue to do it that way if you find that to be faster. So you do have options for it. Now, of course, we're going to answer the idea of domain and range. Remember, does it go left forever? Yes. That's why it's slanted. Does it go right forever? Yes. So my domain, just like before, continues to be all real numbers. My range, well, does it go up forever? Yes. Look at that. But does it go down forever? The answer is no. So as soon as we said yes to going up forever, well then, I'm going to say up forever, that means y is greater. Make a note if you need to. Greater means it goes up forever. And then the lowest y is actually 0, so there's my 0. And then they did say, all right, you got to describe your transformation. Well, remember, we kind of wrote it here, vertical stretch, and it was by a factor of 2. Well, that's exactly what I'm going to write down here. This was just a vertical stretch. They want me to describe it. So it's a vertical stretch by a factor of 2. That just means that's what I multiplied everybody by. But again, we do have options, right? You can either use the points like this and do a little multiplication, or use what we did in the past, where the a value, we almost treated it like slope, almost like slope. Okay, so now here we go. One more, and then we'll take another little pause here so you can try a couple problems. Now, for this one, I look at it. Let me look for my parent function. All I have to do for the parent is there's the name, there's the x with a power. No, you do not highlight numbers or negatives. There's my parent function. So, just like last time, for this one, the parent is y equals x squared. And again, you can feel free to write your points if you want to do this multiplication thing, right? So we already know what x squared goes through. 0, 0, 1, 1, negative 1, 1. These are the three basics for pretty much almost a lot of the parent function, especially these two. So here's the parent function, right? It's a parabola that goes up and up and up and up forever and ever and to the side. So there's the parent right there. Not the greatest, but whatever. There's the parent function. Again, you can write your points if you want to. Negative 1, 1, 0, 0, 1, 1. Okay? All right, but now look. My a value. My a value is just a half. So that means this is going to be a vertical, right? Well, it's less than 1, right? It's between 0 and 1, so it's a vertical shrink. And again, you have a couple options. I can just say, you know what, let me just multiply by a half. That's it, multiply by a half, nothing else. So here's my brand new little chart. Again, this is just option number 1. These numbers don't change out here, always the same. 1/2 times 1, 1/2. 0 times anything is 0. 1 times 1/2 is 1/2. So look at what that means. There's 0, 0. Negative 1, and I only go up halfway. Positive 1, and I only go up halfway. And if you wanted to use the old way, this is why people kind of made little mistakes once before. If your a is 1/2, then you put a 1 under it. I know it looks weird. This is how much you go up. You only go halfway up, and then you go 1 over. People always thought, oh, you go 1 up, 2 over. No, no, no. When you're graphing parent functions like this, you always move over 1. It can only be 1. So whatever this number is, as weird as it looks, look, you go up halfway, and then you go up when you go over 1. So it's not 1 over 1 up, 2 over. No, no, no. Those are lines. That's old school. No, this is for drawing. That's why some people like this method instead. So it's up to you. But we do see that it does get wider. Look at that. This parabola does get wider and wider. But that's the one they want me to call h of x. And so now that I look at it, left forever, right forever. Okay, all real numbers. And then my range, well, goes up forever. It doesn't go down forever. Well, then it's going to be just like this one. So all I'm going to do is I'm going to say y is greater than, because it goes up forever, or equal to, and then 0, because that's the lowest value we get. And when they wanted me to describe the transformation, well, it's the same thing I said earlier, except it's a vertical shrink, because it did get wider. It's a vertical shrink, or compression, by a factor of 1/2. All right, so we're going to take a moment again. We're going to pause the video for a little bit so that you can try these problems. We're going to be doing some stretching and shrinking as well. So let's pause the video now. All right, so let's double check your answer there. Should have had something that looks a little like this. Again, this one was a vertical shrink for the parent function y equals the absolute value of x. Now, I did this one without the table. It is a shrink because it is between 0 and 1. And again, remember, whatever your a value is on top, and you only go up halfway like I did here, and always to the right one. That's never going to change with this technique. And so for this one, it's all real numbers. You don't head down forever, so it's y is greater than or equal to 0. And there it is, the official wording, vertical shrink by a factor of 1/2. This one, on the other hand, is very similar. The parent function is the x squared, so there's the parent right here in purple. The 3 in front, that means my a value is 3. Because it's greater than 1, it's a stretch. So I used our old technique. A is equal to 3, put a 1 under it, so it's automatically 3 spaces up. Look at that, 3 up, and always 1 to the right, and of course to the left, because you do need that other point. And then we draw it out. And yes, remember, it doesn't go up forever. This is going left and up. This one is going right and up. And that's why, once again, our domain is all real numbers. Notice a pattern there. It opens up, so y is greater than or equal to 0. And then there's the official wording for a vertical stretch by the factor of 3. All right, so last problem of the day here coming up, besides the you-dos that you'll do in a bit. So we only have one more, and now it's saying, well, okay, well, let's practice them throwing everything at us. So what happens when we have a little bit of everything in the mix? Well, just like last time, we're going to describe the combination of transformations that we're going to do. Here's what they want me to graph. But let's talk about the parent function first. So if they want me to find the parent function, remember, you highlight the letter. Okay, there it is. Highlight the letter. You do not highlight negatives. You do not highlight any other number. So that means the only thing left for me to highlight is that. And so right off the bat, I now see that my parent function, y equals the absolute value of x. And the good thing about that is, well, now I know which points I'm going to start it off with. In fact, I'm going to draw it. I don't need to do anything else yet. So 0, 0, 1, 1, negative 1, 1. And then, of course, we'll do a little sketch here. We won't draw it too big. Just a little one there. So there is the parent function for me. Okay, so just a small version of it. All right, so there's the parent. All right, that's the one we're going to make moves with. So now let's see what they want me to do. Well, first of all, I see this negative in front. And remember, when we see that negative right there, that just means I'm going to flip it. Flip on the x-axis. Oh, getting in the way there of my own work. All right, I'm going to flip it on the x-axis. You know what? Let me give myself more room here. So I'm just going to write it down. I already know the parent. I'm just going to copy it down. Just want to get more room here. So no changes here. Just copying it out. We already know who the parent is anyways. All right, well, now I can actually even do this. So based on this negative right here, all right, now I can give it some color. They want me to describe the transformation. Well, let's start putting it into words, official words. I'm going to reflect across the x-axis. Wow, that sounds a lot like the word wall. That's because it's exactly what it says. So it should be an easy thing to do there. Now, they want me to reflect it. And then if you notice, we have a couple numbers here. So let's see what the numbers are going to do to it. So I have a 5 on the inside. All right, well, let's take care of that 5 on the inside. Well, the 5 on the inside says plus. I'm supposed to think opposite. Well, then I'm going to go left 5 spaces. And then, of course, we've still got that negative 3 back here. Now, this is not inside the function. So since it's not inside the function, we are going to head down 3 spaces. There, I've described it. This is every move that I'm going to make. Now, one of the things that you should be aware of, though, is that before you make this type of move, you should probably take care of reflection first. That's what I like to do, at least. I like to handle reflections first and then do this part. So here's what I'm going to do. I'm going to do a little quick reflection of it. Reflect across the x. So that means this point stays, but these over here, right? These are going to drop 1, 1. So there it is, 1, 1. Now I'm just going to do a little rough sketch again because this is not my final answer. This is just the reflection. So now I'm right here. I'm in red now. This one up here doesn't matter anymore. Okay. Now I'm going to make my moves. I'm going to move left 5, down 3. And remember, I'm doing that to every point that I see there. So I'm going to go left 5. 1, 2, 3, 4, 5. And down 3. 1, 2, 3. There's this first dot right there. Let's do the vertex here. 1, 2, 3, 4, 5. 1, 2, 3. There it is. And of course, look, we already know it's these three little dots, so then we know the other dot has to be here. And just like that, I'm done, everybody. There is my brand new answer. By the way, remember, we can also think of this as a vertex. When they said left 5, well, that's negative 5. Down 3, negative 3. Well, look, no surprise at this point right here is negative 5, negative 3. So you could also just think of it as a point and draw it and go off of that. But this function right here is the one they want me to call g of x. All right, well, it's time for my domain. Oh, this one is going to get more interesting. Does it go to the left forever? Yes. Left and down, it says. Does it go to the right forever? Absolutely it does. So my domain, look, all real numbers. All right, here's the only one you got to watch out for. The question is, does it go up forever? The answer is no. So then I'm going to say a y right here for my range. It doesn't go up. It does go down forever. Then that means it's less than or equal to. And now here comes the big number. Remember, I'm looking for a y value, not an x. So when I'm looking at this point, well, look at the y value we wrote. It says negative 3. That's the lowest. Or sorry, that's the highest this graph went. So negative 3. And there it is. And this is why it's important to write your vertex, right? If you write it as a point, then now you know what number also belongs with your range. All right, everybody, with that said, you're going to give number 6 a quick try at the bottom, and then just jump right into the homework. With that said, have a wonderful day, everybody. Make sure you do the U-try and double check it on the board.